Hello, my name is David Morris. I am a student in Spring 2020 MAE 535. Today I will be demonstrating the Hall effect. First I will begin by explaining the Hall effect. Here we have a voltage applied across a conductor of dimensions L, W, and T, and a uniform magnetic field applied perpendicular to the conductor and voltage. Lorenz's force equation here states that the force on a moving charge is equal to the magnitude of the charge times the electric field plus the cross product of the velocity of the charge and the magnetic field. Before the circuit is turned on, there is no electric field present. Once the circuit is turned on, the charges flowing through the conductor are deflected by the magnetic field until a steady state condition is reached, where the charge buildup on one side of the conductor has produced an electric field, which counteracts the magnetic force to result in a zero net force on new charges flowing into the conductor. At this steady state condition, force equals zero, and we can solve for electric field in the conductor. From page 2.37 of the notes, we know that the voltage due to an electric field, which in this case is the Hall voltage, can be determined by taking the integral of the electric field over the path. In this case, our path is the width of the conductor. Plugging in our result for E, we get that the Hall voltage is equal to the velocity of the charges times the magnetic field times the width of the conductor. Going a step further, we know from page 2.48 of the notes that current is a function of charge velocity. Rearranging this equation and substituting it into our Hall voltage equation allows us to determine the Hall voltage if we know current, magnetic flux density, conductor material, and conductor size. Let's try this out with a piece of copper. Let's try a simple circuit here. We see a current reading of about 30 amps, but no voltage across this plate. Let's see what happened by checking the math for this circuit. Using the equation we derived, we see the Hall voltage for this copper plate is very low. Let's look at how industrial Hall effect sensors are made. Industrial Hall effect sensors are made using semiconductors and include voltage amplifiers to ensure a usable output voltage level. These sensors are available with digital or analog outputs. Here I will discuss analog output sensors and will show the use of two different sensors from Texas Instruments 5053 series. These sensors output 1 volt when under no magnetic field. You can see the sensitivity levels of the sensors as the slope of each line. Negative versus positive sensitivities dictate the response of the sensor to different magnetic poles. Here's a Series 5053 Hall effect sensor in action. The output voltage will increase or decrease in the presence of the magnet until the field saturates the sensor. The magnetic flux density that causes saturation depends upon the sensitivity level of the sensor. But for this series, saturation always corresponds to a low output of around 0.2 volts and a high output around 1.8 volts. Voltage readings beyond this level occur but are not in the usable range due to the nonlinear behavior of the sensor when saturated. Here I demonstrate how a Hall effect sensor can be used to determine the fluid level in a storage tank. We have a magnet suspended from a float which is located in our tank. Directly below the magnet we have our Hall effect sensor on the edge of the breadboard. The multimeter is set up to read the output voltage from the sensor. This tank is currently empty and the magnet is hanging at its highest position far from the sensor. We see a reading of 1.02 volts. As water is added, the magnet begins to descend towards the sensor. Magnetic flux density increases exponentially as distance from the magnet decreases. This explains why we see the voltage increase at an exponential rate as the distance between the magnet and the sensor decreases linearly. Our final reading is around 1.78 volts. Here's a demonstration using another sensor with a different sensitivity level and magnet orientation. The sensor is located above the glass of water in this setup and the magnet is taped to the top of the float. As the water level drops, we see the voltage increases. For an industrial fluid level sensing system, additional processing of the output could be done, taking into account the exponential behavior of magnetic flux density with respect to distance, to provide a linear fluid level response from a nonlinear voltage response. Recording voltage outputs at specific distances and comparing these to the reported sensitivity of the sensor allows us to linearize our water level voltage data into a fluid level plot as shown here. With the measurements we recorded, we get a fairly straight line that drops off sharply as the magnet gets further from the sensor. This is due to the exponentially lower response far from the sensor. In an industrial application, this can be accounted for by ensuring the empty level of the tank and the sensitivity of the selected sensor allow for a higher output throughout the range of the tank. For this sensor, we would select a tank 80 millimeters deep or less, which would produce the results shown here. With the wide variety of Hall effect sensors that are produced, the Hall effect can be used for other applications including proximity sensing, detection of ferrous metals, alarm systems, current sensing, magnetic levitation, phone and aircraft compasses, and much more. An advantage of Hall effect sensors is they are non-contact and do not experience mechanical wear like other sensors may. I hope this presentation was enjoyable and that you learned more about the Hall effect from it. Thanks for watching.